Alrighty, lads and ladies, welcome back. Sorry for the abrupt post of the link there. I'm just trying to do entirely too much at once today. Last time we talked about improper integrals, specifically type 1 improper integrals. Today we're going to talk a little bit more about type 1 integrals, and we're also going to introduce this new thing called a type 2 improper integral and a theorem that will allow you to determine whether an integral converges or diverges in certain cases without doing the computation, just by comparing to another integral. I'm going to give a few minutes for people to trickle in because I was late posting the link. It got up, like, I think exactly at 11:10. And then we will begin. All right. So here we go. One of these pens is working, one of them is irritatingly dead. So this is MAC2312, section number 004, which is Calc 2. And the date today is the 11th, is that right? Yeah. Okay, and today, we're going to do more improper integrals. Which is still section 7.8. Specifically, we're going to talk about type 2 integrals. Which can be a little bit more subtle than type 1 integrals. So type 1 integrals, the kind that we introduced last time, where you're integrating from like somewhere up to infinity or from negative infinity up to somewhere. It's always obvious that those are improper because there's an infinity written there. Type 2 integrals, there's no such hint. The other thing we're going to talk about here is something called a comparison test. Or comparison theorem. For improper integrals. And that test, or a theorem, the comparison test I'm going to give you, is going to mark a transition in this class, where we go from direct calculation to making logical arguments and indirect work. You'll notice that there's a switch from writing lots and lots of math symbols to writing like complete sentences and working with inequalities. That's because for a lot of these convergence objects, we can't actually evaluate them. For many improper integrals, coming up with the exact answer is incredibly hard. But if you're okay with just knowing whether the integral converges or diverges, there are some workarounds, and that's what I mean by indirect. There are some theorems, some tests that can tell us when an integral converges or diverges without doing the direct calculation. And we use those in the situations where the direct calculation is either impossible or just too hard. But before we do any of that, I just want to talk about type 2 integrals for a little bit. At the outset, let me just remind you of a couple things. So type 1 improper, I need an abbreviation for improper integrals. Type 1 improper integrals are expressions like integral a to infinity f of x dx, or integral negative infinity up to a f of x dx, or integral negative infinity to infinity f of x dx, where f of x is continuous on the interval of integration. So for this guy, continuous from a to infinity. For this guy, continuous negative infinity to a. For this guy, continuous everywhere. Continuous on the interval of integration Right? That's what a type 1 integral is. A type 2 integral is one where we relax this requirement that the function be continuous. In fact, what makes a type 2 integral is that the function has an infinite discontinuity somewhere between like a and b. And then, of course, it's possible to mix the two together. You could integrate a discontinuous function, like 1 over x, from negative infinity to infinity, and then you'd have both type 1 and type 2 stuff. I just want to remind you what a type 1 integral is, because I'll be referring to them. The other thing I want to remind you is that theorem we proved on p integrals. P integrals are a specific family of type 1 improper integrals stuff of the form integral a to infinity 1 over x to the p dx, where a is a positive number. And our theorem, we proved that p integrals converge if p is bigger than 1 and diverge if p is less than or equal to 1. Okay. So just kind of the highlights from last time, because we're going to refer back to these things quite a bit today, and actually for several months to come, or weeks to come. Any questions about what makes a type 1 improper integral, or what a p integral is and when they converge? Okay. So we saw some examples of integrals like these last time. We didn't see any examples of integrals like these last time. So I want to do a couple things here at the start just to sort of warm us up. I'm going to look at an integral like this, where the function inside is slightly strange, because I think there's a problem in your homework that probably most people are going to struggle with just because they don't remember a certain antiderivative. So I want to share that with you to get you over that hurdle. And then I want to look at a type 1 integral of this nature. And show you how that needs to be handled, because there are some subtleties when integrating from negative infinity to positive infinity. So we're going to begin just with a little warm-up. I will ask for some amount of participation here. I'd like to integrate from negative infinity up to 1, the function 6 to the x dx. And to remind you how this is done, integral from negative infinity to 1, 6 to the x dx is a type 1 improper integral, which means we need to write it as a limit. We'll write this as lim t to negative infinity, integral t to 1, 6 to the x dx. Right? Because the problem there is that the lower bound is infinite, and I cannot construct a Riemann sum for any such integral, so I don't have the fundamental theorem of calculus. I can't do any sort of the tricks that we're familiar with from chapter 7. Oh, I'm sorry, there's something in the chat there. Oh yes, sorry. Just a minute more here. We can linger here for a second. While we're waiting, does anybody remember the derivative of 6 to the x? Okay. So we're going to need an antiderivative to solve this problem. Before I talk about the antiderivative for 6 to the x, can anybody tell me just the regular derivative? Yeah, very good. So off to the side here, I'm going to say recall that d dx of 6 to the x would be 6 to the x times the natural log of 6. And generally, d dx of b to the x, where b is any positive base, is b to the x times the natural log of b. So these are two kind of derivatives, or really just one derivative, that you may not have seen in a while. And a consequence of this is that the antiderivative of b to the x dx, like if I'm thinking of an integral without bounds, so my brain is just mush right now. This would be, we kind of need to undo this process, right? And since the natural log of b is a constant, this would be b to the x divided by the natural log of b plus a constant. Right, so the indefinite integral of a non-natural exponential, an exponential where the base is something other than e, you don't just get that thing back, you get that thing divided by the natural log of the base. This is definitely a Calc 1 thing, but I know a lot of Calc 1 classes, even if you see it, you probably don't have a lot of problems on it because it just doesn't show up that much. But clearly we need the bottom statement in order to solve this problem. So continuing over here, this will be limit as t goes to negative infinity. Antiderivative of 6 to the x following this second blue formula is going to be 6 to the x divided by the natural log of 6. And we need to evaluate this from t up to 1. The natural log of 6 is just a number, right? It's it's somewhere in the neighborhood of 1.8 or something like that. But it's just a number. And since that is a constant, it can come out. Just remember it's downstairs, so it's going to come out as 1 over the natural log of 6. And then we have left limit t to infinity, t to negative infinity. And then when I plug in the bounds here, this would just be 6 to the x. So evaluating that between 1 and t, that would be 6 to the 1 minus 6 to the t. So I pop out this 1 over natural log of 6 constant here. It comes out like this. Then what's left is 6 to the x, and I need to plug in these bounds. So that's 6 to the 1 minus 6 to the t. 6 to the 1, of course, is 6, but we need to maybe think for a second about this guy. As t goes to negative infinity, what does 6 to the t do? Yeah, Matthew's got it. It's going to 0. 6 to the 1 is 6, of course. And then this other piece is like 6 to the negative infinity. And there's a bunch of ways to get there. You can think about the graph of 6 to the x, or you can think of this as 6 minus 1 over 6 to the positive infinity. And then you can kind of reason your way there with arithmetic. If you take the number 6 and you raise it to an incredibly large power, that's going to be a very, very large number. So this is like 1 over infinity. This is 0. So you get just 1 over the natural log of 6 times 6 minus 0, or 6 over the natural log of 6. And since this is a finite number, right, since the limit defining the integral exists and is finite, we'd say that the integral negative infinity to 1, 6 to the x dx converges to the value 6 over the natural log of 6. In particular, he converges. Okay, so I wanted to show this because I thought it was a good chance that not everybody remembered these blue statements, because while they're not challenging or deep things, they are things that just don't show up a lot. Questions on this? Okay. So there's one other thing I want to do with type 1 stuff before we move on to type 2 stuff, and that's talk about integrals from negative infinity to infinity. So question, how should we handle integral negative infinity to positive infinity of f of x dx, where f is continuous? Question mark, it's not period. Question. And the reason I want to ask this question is because there's kind of two answers, and one of them is dangerous, I guess we could say. Two things appear to make sense. The first could be writing this integral negative infinity to positive infinity as the limit as t approaches positive infinity, integral from negative t to positive t, f of x dx. Right? Just kind of symbolically, that makes sense. But what Elijah said in the chat is actually correct. This is dangerous. And I'll explain why. There is a problem in your textbook that is meant to walk you to the conclusion that this is dangerous. Remember, when I say that an integral converges, that should mean that the area is finite. There are many functions f of x such that this limit would come out to be finite, even though the area being measured is infinite. And I'll let that sit in your brain for a second while I tell you the correct way to do this. The correct way to do this is to write the integral from negative infinity to infinity of f of x dx first as the integral from negative infinity to somewhere. You can pick where. Usually we use 0, but it could be anywhere else. It doesn't matter, just some finite number, f of x dx, plus the integral from that same somewhere to positive infinity of f of x dx. And then treat each of those separately using their own variable. Two different limits. So I could say lim s to negative infinity, integral from s to a, f of x dx, plus lim t to positive infinity, integral a to t, f of x dx. This is the correct way. All right, so just to be clear, don't do this. Please do this instead. This does have some intuitive appeal because if you just plug in the infinity symbol for t here, it looks like this. So maybe it's okay. In some contexts, it would be okay. But in many other contexts, you would end up calling an integral convergent, even though the area bounded by it is infinite. Let me show you what I mean. So why is the first thing dangerous? The first approach, and this is problem 61 in section 7.8, is dangerous because if we take, let me just say f of x equals x, then the integral from negative infinity to infinity of x dx, we were saying we would write as lim t to infinity integral negative t to t of x dx, which would be limit t to infinity 1/2 x squared evaluated from negative t to t, which would be 1/2 limit t to infinity t squared minus the negative of t squared. But negative t all squared is the same as t squared. So this is 1/2 limit t to infinity t squared minus t squared. And this whole thing is 0. Right? T squared minus t squared is 0. So you'd be taking the limit as t goes to infinity of 0. And of course, that's 0. Well, what's fucked up about that is that the area bounded by that function is definitely not finite. It's definitely not finite. What is the area bounded by that function? Well, f of x equals x, that's y equals x. That's a line with slope 1, y-intercept 0. So the area being measured by this integral is all this stuff going on forever and ever and ever in that way, and all of this stuff going on forever and ever and ever in this way. Which is obviously infinite, right? This is not a finite area. So that integral should definitely be a divergent integral. Remember, the intuition behind saying an integral converges means that the area is finite. It means that there is a definite area, and that definite area is finite. But this area is not finite, just this piece is infinite. And also this piece is infinite. What's going on when you integrate like this, doing that first thing, which we said is dangerous and you should not do, is that your integral from negative t to 0 here is canceling with your integral from 0 to t here perfectly. And so as you expand out in this symmetric fashion, you end up getting perfect cancellation at every step. So even though the areas are both infinite, Because you're doing it in this symmetric way where t goes out on both sides from the origin, right? Like I put t here. I'll put negative t here. And as these two triangles expand outward, they cancel perfectly, which leads to us getting this 0, right? The integral from just this integral, negative t to t of x dx, this integral is always 0. So you end up taking the limit as t goes to infinity of 0. But boy, oh boy, is that area not 0, right? That area is infinity. Just this area is infinity. And we really don't want to say that an integral that measures an infinite area is convergent. That is counter to the whole concept that we're dealing with. This is not the only function that behaves like this, by the way. 1 over x behaves like this. X cubed behaves like this. 1 over x cubed behaves like this. There are many functions like this, where if you were to integrate symmetrically, that's what this is called, by the way, and there are people who do it. Andre Vey is a good example, because in certain contexts, it can be a useful thing to think about, but it's not correct. In other words, the mistake here is right here. Right here. When I said that this is equal to this, they're not. This is not equal to this. What this is equal to the integral from negative infinity to 0 done with its own limit plus the integral from 0 to infinity done with its own limit. And both of those limits will come out to infinity. So this is a divergent integral. Okay, so I just wanted to address that. If you're given an integral from negative infinity to infinity, split it up. Split it up into two normal type 1 integrals where only one of the bounds is infinite, and then evaluate both of those separately. Okay. Questions on what we're saying here? Okay. Then we're ready to talk about type 2 integrals. I claim that despite neither of these bounds being infinite, that this integral is still an improper integral in the sense that the area might be infinite. Can anybody tell me why? Yeah, if you plug in 0 for x, the downstairs here is 0. In other words, there's a vertical asymptote. If we look at the graph, y equals 1 over the square root of x. That graph looks like this. So when I say I'm going to integrate that from 0 to 1, I'm saying I'm looking for this area. And this area goes up, 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 and up. This region is infinitely tall. Which means that I cannot just straight up integrate from 0 to 1 using normal Riemann integration techniques, because again, I can't build a Riemann sum. The rectangle whose endpoint would be here is infinitely tall. It's undefined. But there is a way to get around this using limits in the same fashion that we use limits to get around type 1 integrals problems. The trick this time, instead of like dropping a t over here and then sending t to infinity, as I would if I was trying to integrate from 1 to infinity, is to replace the lower bound by t, because that's where the problem is now. So I'm going to think of t as being in here between 0 and 1. And I'm going to find a formula for this purple shaded area. And then I'm going to take a limit as t goes to 0. But I need to be a little bit careful. I want to integrate from 0 to 1, which means I'm dropping my t between 0 and 1. And then I'm going to send t to 0. But that's a one-sided limit. I'm not interested in sending t to 0 from over here. There isn't any part of the graph over here. This function's domain is just 0 to infinity. So I need to send t to 0. Hopefully you remember this notation from Calc 1. From the right. That's limit t to 0 plus. And this is how you handle what are called type 2 improper integrals. I'll formally define them for you in a minute. Let's go ahead and crunch this out though, because this is a nice example. According to the picture I drew below, this is going to be lim t to 0 plus integral t to 1 over the square root of x dx. So, and now this integral is a regular Riemann integral. This is not an improper integral because I understand that t is a little bit to the right of 0. That's lim t to 0 plus integral t to 1. 1 over square root of x, that's x to the negative 1/2. And then your antiderivative step is nothing fancy, it's a power rule. Notice how I'm writing the limit every time. We're not getting sloppy here. Please don't get sloppy. Your antiderivative comes from the power rule. You add 1 to negative 1/2. Negative 1/2 plus 1 is positive 1/2. So it's going to be x to the positive 1/2. And then we need to divide by that new power. Dividing by 1/2 is the same as multiplying by 2. So that's our antiderivative. And this needs to be evaluated between the bounds t and 1. The 2 is a constant, and it can pop out. And we get 2 times limit t to 0 plus. The 1/2 power is a square root, so this is the square root of 1 minus the square root of t. And in order to sort out that limit, I think it's useful to think about the graph, y equals the square root of t, where this is my t-axis. That graph is half of a sideways parabola like this. This is what the square root function looks like. So thinking just about this piece, which is the only place that the variable from my limit shows up, as t goes to 0 from the right, this function goes to 0. So I get 2 times, well, the square root of 1 is 1, and that limit of the square root of t is 0. So this integral comes out to 2. And since that limit exists and is finite, we would say the integral converges. So therefore, the integral from 0 to 1 of 1 over the square root of x dx converges. And we'd say it converges to the value 2. Questions on any of these steps or graphs, limit work, any of that? Okay. I have a quick question for you. Is this a p integral? This is like 1 over x to the 1/2 in here, right? I could write this as 1 over x to the 1/2. Does that make this a p integral? That's correct. The answer is no. Why? So no, right? This is not a p integral. Correct to say no there. The reason it's not a p integral is because it's not going from 1 to infinity, right? P integrals always go from like somewhere to infinity, and that somewhere has to be a positive number. So if this was integral from 1 to infinity of 1 over root x, that would be a p integral. If it was integral 2 to infinity, 1 over root x, that would be a p integral. But integral 0 to 1, not a p integral, because it's not a type 1 integral, right? P integrals are always type 1. Okay. So we said that this is technically a type 2 integral. We haven't formally defined what type 2 integrals are, so let me go ahead and do that. Type 2 improper integral are integrals of the form integral a to b f of x dx, where f of x has an infinite discontinuity. So I can say it differently, somewhere on the interval a to b, closed interval a to b. And the way we handle these is by splitting them up to make that infinite discontinuity at the end point. So more specifically, if f of x has an infinite discontinuity at x equals a, then we define the integral from a to b of f of x dx. We define that type 2 improper integral to be the limit as t approaches a from the right of the integral t to b f of x dx. And this is exactly what we saw in the last example, where that function 1 over root x blew up at x equals 0. So in order to get at the integral, we needed to replace that lower bound where the problem was by a variable t, do the integral from t to 1 or t to b, and then take the limit as t approaches that problem spot, staying within the interval. Sort of the picture here. A is here. And my function has an infinite discontinuity. Infinite discontinuity just means vertical asymptote. And then does, whatever else. And b is here. And this function is blowing up to infinity at a. The integral from a to b is trying to measure all of this area. And there's a problem over here because we're trying to integrate up to this asymptote. And the way we manage it is by plopping t in here, integrating from t to b, and then sending t over towards a from the right. Now the other possibility is if f has an infinite discontinuity at the right endpoint, the upper bound. And in that case, we do the same thing, just we're going to replace the upper bound by our variable t. So this guy would be defined to be equal to the limit as t approaches b. This time we're going to come in from the left. Integral a to t f of x dx. And the picture here and here's b. Here's my infinite discontinuity. Here's a. My integral is trying to measure all the area bounded by f between a and b, which would be all of this stuff, which again, there's a problem, right? Because it goes up forever. That region is infinitely tall. And our workaround is to drop t in here between a and b, find a formula for the area from a to t, and then let t sneak up on b, this time coming in from the left. So people often ask me, why are these limits one-sided and how do I know? Is it going to be like a from the right or from the left thing? You need to think about the picture. The idea is that t needs to stay between a and b. So in order for t to stay in between a and b and also sneak up on the lower bound a, that means he needs to be coming in from the right. If t needs to stay between a and b and sneak up on the upper bound b, that means t needs to be coming in from the left. So if you're ever doubting which kind of one-sided limit do you need here, think about the picture. You could also just say, you could memorize, right, that if the problem is at the lower bound, it's going to be a limit from the right. And if the problem is at the upper bound, it's going to be a limit from the left. But I think the picture tells you these things and gives you some deeper insight, and also then you're not taking up precious space in your brain. There's a possibility we haven't covered here. Right, this type 2 improper integral is something like this, where f has an infinite discontinuity somewhere on the interval ab. Well, a and b are not the only two numbers in that interval. What if the discontinuity is somewhere in the middle. If f of x has an infinite discontinuity at x equals c, where a is less than c is less than b, in other words, somewhere in the interior of that interval, then we split the integral up. And apply the techniques above. To both pieces. So, right, so if I had integral a to b f of x dx, and f has some vertical asymptote between a and b at the number c, then I would split this up as the integral from a to c f of x dx plus the integral from c to b f of x dx. And now this piece is like one of these. And this piece is like one of these. So if the discontinuity is in the middle, just split it up. Split it up and then handle each of the resulting pieces using the techniques for the problem at the end point. I know this is kind of a lot to get down in one moment, so I'll hold here just for a second, trying to get as much of it in the page as I can. Are there any questions we would like to ask about this? Okay, I'm going to hold for about 5 more seconds in case anybody's still writing, and then we're going to look at some examples. All right, here we go. Let's look at the integral from about 1 to 3 of 1 over 3 minus x dx. This function has a problem at x equals 3 because the bottom is equal to 0 there. You can think of this function as a transformation of 1 over x. It's 1 over x shifted to the right by 3 units and then flipped over. But even without knowing the graph, we can set this up. I'll sketch the graph for you very quickly. Mark this as 1, 2, 3. The bottom is 0 at 3, so there's going to be a vertical asymptote there. And the graph of this function looks like this. Oh, actually, nope, god damn it. I did this backwards, didn't I? Yeah, sorry, not this. Looks like this. And So the area we're trying to measure here from 1 to 3 yeah, the area we're trying to measure here is this area. Which goes up and up and up forever. So this might be finite. It might be infinite. The way we handle this is by writing this as limit t goes to 3, and we're thinking of t as being in here. We're going to integrate from 1 to t. One over 3 minus x dx. And because t is between 1 and 3 here, t needs to be sneaking up on 3 from the left. I'm not interested in anything going on over here to the right of 3. All of the area I'm after is between 1 and 3. So this is lim t goes to 3 from the left. And again, if you just want to memorize it, if the problem is at the upper bound, it's going to be a limit from the left. But I prefer thinking about the picture. How do I do this integral? Yeah, it's a little substitution. So we're going to sub z equals 3 minus x, which means the dz is negative dx. We need to change our bounds. This is still a definite integral. I'm still making a substitution in a definite integral, even though it's improper. So my old bounds were 1 to t. Right? These bounds are 1 to t, and we need to use those bounds. So when I make that substitution, z equals 3 minus x. Well, if you plug in 1 for x, you get 3 minus 1, which is 2. And if you plug in t for x, you get z equals 3 minus t. So that's my new upper bound, 3 minus t. The other thing here, because dz is negative dx, we're going to get a negative out of this. So this is going to be lim t goes to 3 from the left, negative integral 2 to 3 minus t, 1 over z dz. Now that negative, it's a factor of -1. It's a constant factor. I can pop it out. Shit, I'm getting a call from the testing center. I'm so sorry, guys. Hey guys, sorry, this is something with the DRC. I actually have to sort it out. It's going to take just 1 second. I apologize. Holy shit, that was annoying. So sometimes when you fill out a testing contract with the DRC, they just straight up fucking lose it and then call you in the middle of class and demand that you take time to walk them through things. So anyway, let's get back to what we were doing. We need to evaluate this integral, which after making our little substitution, turned into lim t to 3 from the left, negative integral 2 to 3 minus t, 1 over z dz. I know that disruption is very distracting, so are there any questions up to here? Are we comfortable with the substitution and why everything changed the way it did? Where the negative came from, where these bounds came from? We're all comfy with the 3 minus t and the 2? Okay. Then we're ready for our antiderivative step. I still have lim t to 3 from the left. We've got this negative out front here, which I'll write as negative and then bracket. Antiderivative for 1 over z is the natural log of the absolute value of z, and we're evaluating this from 2 to 3 minus t. I can pop the negative out past the limit, this negative, and then plug in these bounds, and we'll have the natural log of the absolute value of 3 minus t minus the natural log of 2. And since 2 is positive, we don't need absolute values here, right? The absolute value of 2 is just 2. Oh, just seeing here in the chat now, this negative came from the substitution. In this previous step, we said we want to substitute for the bottom, 3 minus x. So I made the substitution z equals 3 minus x. When we take the differential, the derivative, yeah, dz is negative dx. So that negative is going to pop out here. All right, everything else feel good? So obviously this natural log of 2 piece, that's not a problem. That's like 0.69. That's not an issue of any sort. But the natural log of absolute value of 3 minus t, that might be a problem. Because as t goes to 3, 3 minus t is going to go to 0. What does the natural log function do as its inside goes to 0? Let me just plug this stuff in and we can write it down symbolically and then think about it. So this is going to be the natural log of the absolute value of 0 minus the natural log of 2. And if we think about what the graph of the natural log function looks like, I know from that test that some of us are very comfortable with the graph of the natural log, but not everybody. There is this piece over here, but that's not the whole story. The natural log function also continues down here. Right? This is at 1. So between 0 and 1, the natural log function starts diving down to negative infinity. So this natural log of 0, that's negative infinity. So what we get here is negative infinity minus the natural log of 2. So if you take negative infinity and you subtract natural log of 2, which is about 0.69, you get negative infinity. So this is negative infinity, which is positive infinity. So this integral very much diverges. Integral from 1 to 3 of 1 over 3 minus x dx diverges because the limit defining the integral is infinite. Type 2 integrals, same rules for type 1 integrals. They converge if the limit exists and is finite. They diverge if the limit fails to exist or is not finite. So here this limit came out to infinity, that is not finite. So this integral defined by that limit diverges. questions, comments, concerns? Okay. Let's look at something a little bit more interesting. And then we're going to talk about that theorem. Let's look at the integral from 1 to 5 of 1 over x minus 2 to the 5/3. A problem like this was given to me once on an integration competition. So I think I mentioned to you guys, there's a thing at UF and at MIT and at a few other good universities called an integration bee. It's like a spelling bee, but for integrals. And I remember walking out of there thinking, I whooped so much ass, I did so good. Why did they even give me such a hard problem? Isn't this, or why did they give me such an easy problem? Isn't this supposed to be a challenging problem? Aren't I at a competition? The thing I did wrong is something that I see a lot of people do wrong when they encounter problems like this. I didn't even realize it was an improper integral. Neither of the bounds are infinity. And you could just jump in and start applying the power rule to this. A little substitution, power rule, let's see what happens. So what I'm about to do is wrong. People often ask me, do I need to go through the process of writing out the limit? Can I just treat it like normal? It seems like it works sometimes. Here's why you cannot do that. If you go, okay, integral 1 to 5, 1 over x minus 2 to the 5/3, that's x minus 2 to the negative 5/3 dx. I can do a little substitution. Z equals x minus 2, dz is dx. Change my bounds because I'm a good calculus student. So when x is equal to 1, z would be equal to 1 minus 2 is -1. When x is equal to 5, z would be equal to 5 minus 2 is 3. So this is going to become the integral from -1 to 3 of z to the negative 5/3 dz. And then I can say, okay, well, power rule, -5/3 plus 1. If I add 1 to 5/3, that's adding 3/3. That's going to be -2/3. So the z to the -2/3 divided by -2/3 or times -3/2. Evaluated between these new bounds, -1 to 3. So that is, what is that? -3/2 times -1 to the -2/3 minus 3 to the -2/3. And then you can say, okay, well, that's -3/2. -1 to the -2/3. That's the cube root of -1, which is -1 squared, which is +1, all over 1. So this is 1 minus, this would be 1 over the cube root of 9. And I declare victory and say, yeah, I nailed it. I got this. I did perfect. Why did they give me such an easy problem? This shit is wrong. It's not even wrong by a little bit. It's wrong by a lot. But the steps all look good. What's wrong? Why is this wrong? Yeah. This function has a vertical asymptote at x equals 2. Not only is this not the answer, the answer isn't even a number. This is a divergent integral. What we need to do Let's take the integral from 1 to 5 of 1 over x minus 2 to the 5/3 dx and split it up. The problem is in between the bounds. It's not at either of the bounds themselves. I can write this as the integral from 1 to 2 of 1 over x minus 2 to the 5/3 dx plus the integral from 2 to 5, 1 over x minus 2 to the 5/3 dx. And then you need to treat each of those separately with their own limit. So I'll go ahead and work on the first piece. We'll see what we get with this piece. The integral from 1 to 2 of 1 over x minus 2 to the 5/3 dx is a normal type 2 improper integral, right? The bottom is 0 when you plug in 2. 2 is the upper bound here. So I can write this as the limit as t approaches 2 from the left, integral 1 to t, and then x minus 2 to the 5/3 downstairs is x minus 2 to the negative 5/3 dx upstairs. There's nothing wrong with the antiderivative work here. That was all fine. It was just not treating it as an improper integral. You need to be careful with these things. I will make our substitution in here. So I'm going to let z be x minus 2. dz is dx, just as before. I need to change my bounds. My old lower bound is 1 here. So when x is equal to 1, z is going to be 1 minus 2 is negative 1. When x is equal to t, z is going to be t minus 2. So this becomes the integral from negative 1 to t minus 2 of z to the negative 5/3 dz. Which is lim t to 2 from the left. Antiderivative step here was fine before. It's negative 3/2 z to the negative 2/3. And we're evaluating from negative 1 up to t minus 2. The negative 3/2 can pop out. Still have limit t to 2 from the left. And when I plug in those bounds, we have t minus 2 to the negative 2/3 minus negative 1 to the negative 2/3. Now the negative 1 to the negative 2/3 really isn't a problem. You may need to think about it for a minute. If this were positive 2/3, that would be the cube root of negative 1 squared. So the cube root of negative 1 is negative 1. When you square negative 1, you get positive 1. So this is 1 over positive 1, which is 1. So this whole piece right here, this is 1. The other piece, though, let's actually write this as a fraction. This is 1 over t minus 2 to the 2/3. This piece we said was 1. So as t goes to 2 from the left or the right, but specifically as t goes to 2 from the left, this bottom is still going to 0. Now you need to think a little bit about whether that's going to mean this thing goes to positive infinity or negative infinity. So if this bottom, if t is very, very close to 2, but a little bit smaller than 2, then this is a very small negative number. It's like 0.001. Negative 0.001. When you take the cube root of that, it's going to stay close to 0 and negative. When you square that, it's going to become positive. So this is negative 3/2 times 1 over a very, very small positive number, positive infinity. So we end up with negative 3/2 times infinity minus 1. Infinity minus 1 is still infinity. So this is negative infinity. And that's it. That's this first part done. So what we've seen here that the integral from 1 to 2 of 1 over x minus 2 to the 5/3 dx diverges. And I shared with you last time a very important fact about improper integrals. If any part of an improper integral diverges, then the whole improper integral diverges. We'll just restate that. Any part of an improper integral diverges, then the whole improper integral diverges. So I have not yet shown that the original problem is a divergent integral. The original problem was the integral from 1 to 5. What I just showed is that the integral from 1 to 2 diverges, right? That's what we were working with to get this. So since the integral from 1 to 2 of 1 over x minus 2 to the 5/3 dx diverges, it follows from the fact that the whole integral, the integral from 1 to 5, 1 over x minus 2 to the 5/3 dx diverges. And that's the full solution. We really do need this last observation. I don't know, we might be having connection problems. Let me turn off my video, I'll lower the bandwidth requirements. So let's think about what we did here in totality. The original integral, the integral from 1 to 5, we had to split that up because the problem for this function is at 2, and 2 is between 1 and 5. So I split this up as the integral from 1 to 2 plus the integral from 2 to 5. I haven't done jack shit with this piece yet, but I calculated this piece. I was able to show, just working with the integral from 1 to 2, that piece diverges. The integral from 1 to 2 diverges. And then we have this fact that says if any part of an improper integral diverges, then the whole improper integral diverges. So just from this piece being divergent, I can conclude that the whole thing, the integral from 1 to 5, is divergent. So we're done. I never even had to touch the integral from 2 to 5. Just by working with the integral from 1 to 2, I was able to discover that the entire thing, the integral from 1 to 5, all of it diverges. Even if the integral from 2 to 5 converged, the whole integral would still diverge because, some infinity plus something finite is still infinity. So this fact can be a big time saver. If you're looking at a big, scary, improper integral, You split it up into several different improper integrals. As soon as you find one piece that diverges, you can conclude that the whole thing diverges. Now, the converse is not true. If one piece converges, that doesn't mean the whole thing converges. But if one piece diverges, it is true that the whole thing diverges. Questions on this? Okay, I'm aware that we've gone over time here. I understand if you have to go, you have to go. But because we had that DRC call interrupt us, taking a good chunk of time, there's one more thing that you need to work the homework and that I need to share with you here today. So if you gotta go, you gotta go. I get it. YouTube video will be up shortly. Just watch the last few minutes of that. And, with apologies, I'm going to now share with you that comparison theorem. What this says is if 0 is less than or equal to f of x is less than or equal to g of x on the interval a to infinity, then two things are true. If the integral from a to infinity of g of x dx converges, then the integral from a to infinity of f of x dx converges. So if the integral of the bigger function is finite, then the integral of the smaller function must also be finite. Can't really move the office hour now, but we'll be done here in just a second. I have a class right after the office hour too. The second thing which is true here is that if the integral from a to infinity of f of x dx diverges, we'll be done well before 1, then the integral from a to infinity of g of x dx diverges. So if the integral of the larger function g is finite, then the integral of the smaller function f must also be finite. In terms of areas, what we're saying is, it is, I'm not answering. So what we're saying here is if the green area is finite, then the purple area has to be finite because the purple area fits inside the green area. So the purple area has to be smaller. And if you're smaller than something finite, you have to be finite. And sort of the other side of this if I tell you that the purple area is infinite, then the green area has to be infinite because the purple area fits inside the green area, which means the green area is bigger than the purple area. That's what this says. And I want to show you one quick example, and then we will end. I'm so sorry for all these disruptions. I don't know what the fuck's going on at the DRC these days. Let's determine whether the integral from 1 to infinity of cos squared x over x squared dx converges or diverges. Now I'll tell you what we're not going to do. We're not going to calculate this integral. You will never, no matter how hard you try, find an antiderivative for cos squared x over x squared. It cannot be done. Is the screen share fucking up? All right. We're trying to crunch this out. The picture there. If the purple area is infinite, the green area must be infinite because the green area is bigger than the purple area. And the other way of thinking here, if the purple area is finite, then the green area must be finite because the green area fits inside the purple area. So we want to figure out whether this integral converges or diverges, but we're not going to calculate an antiderivative for this thing. We can't do it. It doesn't exist. And there are a lot of functions like that. But what we can do is come up with an inequality like this and appeal to our comparison theorem. We know that cosine is always stuck between -1 and 1. The cosine function is a wave that bounces back and forth from -1 to 1. Those outputs are never larger than 1, never smaller than -1. Because of that, cosine squared is always going to be between 0 and 1. If you take numbers that live between -1 and 1 and square them, they'll become positive, but they'll still never get bigger than 1. Dividing through by x squared we arrive at this inequality. And in a sense, this is a lot like the squeeze theorem, where you're going to build up an inequality that will allow you to appeal to some theorem. But rather than trying to squeeze one function between two other functions, you're just trying to squeeze one function underneath another. This inequality is now very similar to this inequality. And this is true for all x's greater than 0. But I'm particularly interested in the interval from 1 to infinity. So this, I will note, is true on the interval 1 to infinity. Now, if I can show that the integral of the larger function converges, we can conclude that the integral of the smaller function converges. Stockholm. Moreover, we know that the integral from 1 to infinity of 1 over x squared dx, this is a p integral. With p equal to 2. And we know p integrals converge if p is bigger than 1. 2 is bigger than 1. So this integral converges. Therefore, by our inequality and the comparison theorem, the integral of cos squared x over x squared must also converge, because cos squared x over x squared is smaller than 1 over x squared. Now I'm going to stop here, but with a little comment. This style of problem solving is very different than the style of problem solving that we've seen throughout the semester elsewhere. I didn't even attempt to calculate the integral. What we did do is kind of circumnavigate that calculation by coming up with an inequality and then making a logical argument that depends on the comparison theorem. Throughout the rest of this kind of middle part of the class where we're talking about convergence, the problem solving will feel more like this and less like what we've been doing up to this point. In your homework, for the problems that talk about the comparison theorem, you're just going to be asked to say whether the thing converges or diverges. And I know it's easy to just click, you guess twice, you're going to get it. If you do that going through the homework, you're not going to be prepared for the test. What you must do is practice writing out solutions like this. Don't skip the words. The words are what make the solution here. It's the logic. This is not about calculation anymore. It's about the logic and appealing correctly to the theorem. So there's kind of a skill here in building the inequalities is something you probably haven't seen since the squeeze theorem. And I know the squeeze theorem is not always given the love it deserves in Calc 1. So you need to practice building up these inequalities. And then the other thing you need to practice, the new skill here, is writing out these words and constructing careful logical arguments. We're going to be doing this with improper integrals. We're going to be doing this with sequences. We're going to be doing this with series. And that's like the next month and a half of the class. It's a lot of stuff that leans on this style of argument. So take the time as you solve the problems and make sure you're writing out good solutions. Just clicking converge or diverge doesn't teach you anything. It really doesn't. The problems in the textbook are very, very good. So when I assign the homework, I'm putting together a minimal problem set to prepare you for the test. And if you solve those problems as they're intended to be solved, that is enough. But if you feel at all insecure about your skills as the test approaches, you should come into the textbook and start looking for some more challenging problems. So I gave you, I think, like 2 of these, right? These are using the comparison theorem. And all WebAssign is going to ask you to do is click converge or click diverge. And I know how easy it is to do that and just move on without thinking about it too hard. But please promise me that you will spend the time on those problems to really understand what's happening and why they work. Build up the inequalities. Write down the words in full sentences, the logic. There are other really good problems in here to help warm you up to the concepts we're playing with. Things like number 61 we did in class today. All the other kind of logic-based problems here are very, very good. Number 76 is excellent. 82 is very good. The questions that pertain to improper integrals here in the concept check and true false are also very good. So please spend the time really working on and thinking about this stuff. I know everybody needs the homework grades to feel comfortable. And if at some point you find yourself doing that thing where you just click one or the other until you get it right, that's not the end of the world, but you must at some point spend the time practicing this shit. So that's all. I'm happy to work with you on it. I want you to spend time working on it. I really want everybody to do well here. Just know that clicking to get the right answer in WebAssign is not the same as studying this stuff. This stuff requires logic and careful practice. So we've gone way over time here, and I'm sorry for that, but this is something that I wanted to get out while we were here today. So I'm going to apply to all the previous problems on 7.8. You could. Now, I would say that most of the previous problems in 7.8 are easier to solve just by going in and grinding them out. But some of the problems back there, especially the harder ones, yeah, you could apply this logic to say whether the integral converges or diverges. But most of those problems ask you to find the value of the integral also, right? So if the integral converges, you need to tell me what it's equal to. This theorem won't do that for you. Right? This theorem will not tell you what the value of the integral is. It just tells you that the integral converges. So yes, you could apply it, but in many of those problems, it won't give you the full answer. It'll just give you part of the answer. All right, these DRC people are still blowing up my phone. They must be having a hard time with something else. So I'm going to end the meeting here. Office hour at 1 p.m. If you need to take the makeup test, today is the day. Come to the office hour at 1. I'll see you there. Otherwise, I'll see you guys on Monday. Take care.